So my talk has two parts. The first is something about Karl-Einstein metric and case stability. I will give a survey of this topic and introduce some main theorems. And the second part, I will focus on one part of this this entire program, and which I mean is somewhat more technical part. So as you already saw yesterday in Karina's talk, I mean this entire story was started actually by different geometers attempted to try to find a canonical metric, which in this case is called a Karl-Einstein metric. So basically you start with a complex manifold. So for if you have a Hermitian metric, I mean Kähler in his paper which invented the notion of a Kähler metric, he already asked this question. Basically, first he defined a Kähler metric as locally can be written as this way. So F is a potential of this Kähler metric, and then he asked, he defined now this what we call Kähler metric, which I mean of course we know attach a form omega g, and it's Kähler if and only if it's a closed form. And then Kähler himself in his original paper, but later this problem was I think advertised by Calabi in 50s, is find a metric omega such that the rich omega is equal to lambda omega for some constant lambda. And as you saw yesterday, we know that the class of the rich omega, no matter which omega Kähler metric you start with, is a Chern class. So in other words, the Chern class has to be proportional to the Kähler class. In other words, the Chern class is either ample, zero, or negative or anti-ample. So that's a consequence, immediate consequence from this equation. And of course, when dimension one, we know this follows from Poincare uniformization theorem, and people made a big progress in 70s for the two cases when lambda is equal to 0 and lambda equal to -1. This was solved by Yao and also Aban Yao independently. But the most tricky case is when lambda is equal to 1, because this is not always true. So in this case, we know that we call it final. Remember, lambda is equal to 1. That means that C1 of X is ample. So in other words, the canonical class is anti-ample. I mean, we all call them final variety. And Matsushima found the obstruction in 50s that if X has Karl-Einstein, then the automorphism has to be reductive. I mean, you heard this in Karina's talk. So, but anyway, the goal now is we want to characterize when this has a solution. For what kind of final manifold or final variety, rich omega is equal to omega has a solution. I mean, clearly this might not be the if and only if condition. So, but actually there is a more ambitious goal behind that. Instead of studying them one by one, we actually want to parameterize them using a good modular space. Here, good is just a vague term. It will become a mathematical term later. I mean, so of course, different geometers, they also have some idea to parameterize this all Karl-Einstein metric to move them in a family, and we algebra geometers will have our own way to think about this. So let's take a quick look at how people start to solve this kind of problem. So for Didi-Bar, we know by Didi-Bar lemma that if I have a two Kähler form, if they are in the same class, then the difference can be written as Didi-Bar phi for some function phi. So now if I start with any metric which is in the right class, in other words, omega 0, the class is in the Chern class, then for any other metric, omega minus omega 0, you can write it as a Didi-Bar phi. And because this omega 0 is in the Chern class, of course, its difference with its own range can be also can be written as Didi-Bar f. If f is 0, then we got our Karl-Einstein metric, but usually we are not so lucky to start with the Karl-Einstein metric. So then you just turn this equation into some a complex Mann-Zampe equation. So this kind of a determinant of a Hessian is usually called the Mann-Zampe equation, and here we are in a complex setting, so it's called a complex Mann-Zampe equation. And you want to solve this equation. Of course, you look at all the possible phi. So this is the space which Carolina also defined yesterday, the infinite dimensional space of Kähler potential with the same class. And Mabuchi in '86, following like Donaldson's work on the solution of Hitchin Kobayashi correspondence, he also defined some like an energy functional, which nowadays we call he called it K energy functional. I think that's probably where the K stability, the K star was started, this letter. But nowadays I think people more call it a Mabuchi functional. That and he showed that the critical point of this functional is a solution of Manzampe equation. In other words, it gives you a Kähler-Einstein metric. But of course, now the problem become in an infinite dimensional space. I want to find the critical point of some functional, which is pretty, I mean, classical setting for people solving PDE, nonlinear PDE. So now let's look at the toy model babysitting, which basically is called the GIT, geometric invariant theory. So now we consider some like a reductive group, which is a compactification of some compact group K. K here is a real compact group. And we pick up a norm, which is K invariant. I mean, you can do this because K is a compact group. And for any point X, you find the lifting X hat in LX. And now I define a function. For this fixed X, I define a function by sending element from the group G to real function, by sending element G to the norm of G acts on X hat and take a log. And because this is K invariant, this function is actually defined on G mod K. So I have this space of G mod K and I define a function. This function depends on X. And now, I mean, this space G mod K, it has lots of geodesics. I mean, one type of geodesic is given by the C star mapped to this, some like a one prime subgroup. And then if you walk along this C star, you take the derivative and the infinite of this function, you get a weight. And this weight is precisely the C star weight on if you restrict your line bundle on the limiting point of X. And then of course the X0 becomes a fixed point. And then the action, you get a one dimensional representation of your group, of your C star action, and that will give you a weight. So this like seems to be analytical number is actually has an algebraic interpretation, and this is the weight. So now you ask yourself, when F has a unique minimum, so this is basically the problem related to the variation, I mean the problem for similar to the Kähler-Einstein problem. We have a functional, we have a undefined space, we ask ourselves when we has a minimum. So you know, F has a minimum, so you think, well, it's not very hard to prove this function is kind of convex. So then when you're going to go to infinity, if your function goes like this, then of course it has a minimum in the middle. But if your function goes like this, then there is no minimum. So in other words, you have to look at the derivative under the infinite place. And you look at the derivative along all the directions. If they are all positive, then it's not very hard to prove you have a minimum. So this is the first equivalence here. And so remember the derivative, the geodesic is given by this kind of data. But when it's rational, then we got some algebraic data. But then the second equivalent to say, you look at all the like a possibly irrational direction, all the direction is actually equivalent to you only look at the rational direction. And the rational direction you get algebraic data. So that's a second equivalence. And of course the third equivalence, that's just the famous Hilbert-Mumford that if we know all the weighted positive, then my point is stable, then it's actually in a moduli space. So somehow this, you say this kind of relationship between the minimum, existence of minimum for some functional, and then you going through all this kind of equivalence, and at the end of the day, you get some like a, you get some like a moduli problem in algebraic geometry. So that's how this thing was set up. But this is just the toy model that GIT is. So now let's go back to our infinite dimensional problem of solving Kähler-Einstein problem. So somehow because of this kind of similarity of solving Kallenstein and the GIT, people were trying to use the framework of GIT to study the algebraic corresponding problem in early 2000. But that turns out to be, not so successful. I think the more successful way was trying to do it through the framework of minimum model program. And this was some like early progress along this direction. So Odaka, I think around 2011, he realized that the k-stability of some variety will actually have some implication of the variety has some kind of a Bayesian type singularity. So that was where the first, I think, the Bayesian geometry showing up. And then Chile and us, we somehow initiated a theory called, you just have to test on special objects. And Berman later introduced another functional called the Ding functional, which replaced the Mabuchi functional, but has the same property. Actually, the Ding functional was basically introduced by Ding, or maybe even earlier. But Berman did the same thing to attach a Ding invariant for the Ding functional, which is like a Futaki invariant attached to Mabuchi functional. And he showed that for final variety, this is also enough to test the Kallenstein metric. But somehow the Ding functional, from the algebraic geometry viewpoint, the Ding stability, the Ding invariant has better properties than Futaki invariant because essentially it only involves low current threshold and the volume, which are two terms which we study very well. And from a different geometry viewpoint, there is also a reason why for final variety, Ding stability is easier to study than the original K stability. But anyway, Fujita, he showed that the actual Ding stability is equivalent to K stability. So basically, he showed this by showing that both of them, you can just following the Chile and my work to show that both of them, you can only test them on this kind of special objects. But on special objects, they're just the same. So this way you get they are actually equivalent. And also Fujita, another important result Fujita showed was Ding invariant actually has much better approximating properties. So you can play it more easily. But all this early progress was basically crowned by this like a Fujita-Lee criterion. Yesterday you heard it in Carolina's talk. But let me just define this terms again quickly. So we use A to be log discrepancy. Here I think everybody know what log discrepancy is. So in our talk, we only consider final variety with KLT singularity. So the log discrepancy is always positive. And then we have this second, more mysterious term, which is called the expected vanishing order. So basically you look at the adding divided E, which is over X. So it's not necessarily on X, but it's on some Bayesian model on X. Then you look at the volume, here. And so for different T, the volume get, you can think about it, it's kind of like a expected vanishing, amount of vanishing with T. So then you take the integral. The integral is actually finite integral because once you pass through the pseudo-effective threshold, of course it becomes 0. And then you take the average by the volume. So this is expected vanishing order. Then we define the stability function or stability threshold, delta X, to be the infimum of A over S among all the E. So here the delta actually has a different geometry interpretation that if delta is less or equal to 1, then the delta here is actually precisely the supremum of you solve this reach omega equal to T omega plus 1 minus T omega 0. Remember, omega 0 was this like a background metric, the metric I start with. So if this T is equal to 1, then I basically solve this Kallenstein equation. And when T is equal to 0, that's, you can just always find such omega by applying Calabi conjecture. So by Yau's proof of Calabi conjecture. So you can start with this process and you start to increase T. The where you stop is, sorry? This S, it's hard to say where I think it was invented by in Chile and Fujita's paper. If you look at the other math literature, the S appeared a little bit in the Liouville theory. I mean, in this, like people study the Diophantine equation, but somehow the interplay is, the relationship is not so clear to me. Well, okay. If the S is, I mean, if this is finite generated, then it's much easier. I mean, if the gradient ring is finite generated, it's much easier. But the point is, for instance, if the E is finite generated, the A minus S is precisely the Fataki invariant. So that was how, for instance, I think Fujita and Chili first proved that on special object, this A minus S, this invariant is the same as the Fataki invariant. But so in general, this, I mean, then probably from there, it's not so imaginative to consider all the S. Sorry? Mm-hmm. Yeah, sorry, there exists omega such that is true. Yes, thank you. Yeah. Such that this is true. Oh, sorry. I think this was, I mean, this was actually later after the delta was invented. I think this was proved in a paper by Rubinstein, Koei Zhang, and maybe also Chertsov. But I think this was more or less already in the literature before. But so it was also, sorry, in Berman Buxton-Johnson's paper. Yeah. But this was especially realized like after the delta was written out. But anyway, so when Fujita and Lee invented this delta, actually, sorry, maybe I should give more precise credit. This delta was first defined by Fujita and Odaka, but it was not defined in this kind of form. I mean, then to prove this kind of form is the same as the original form that was in a paper of Buxton-Janssen. But to show that this delta can be used to test the case stability, that was actually just relying on some like earlier result by Fujita-Lee. That's why I call it the Fujita-Lee criteria. So the main content that this invariant can be used to test the case stability, that was in Fujita and Lee's work. So now we have this two, so basically you can use this as a definition of this. I mean, this was not the way people defined it before. People defined before use test configuration. You saw it in Karina's work, but I think now maybe now it's more natural to look at this delta, that delta x is larger than 1. We call it a uniform case stability. And its case stability if and only if for this A over S is larger than 1. Of course, when you take an infimum, it could happen that each of this term is larger than 1, but the infimum is 1. That's something we want to avoid. And that's exactly what we show. So Yuchen Liu and myself and Zhiquan Zhuang, we show that when delta x is less than n plus 1 over n, so if delta is larger than n plus 1 over n, I mean, of course, everything is, I mean, from the case stability viewpoint, we already know it's uniform case stability has Karen's metric. There's nothing to worry about that. So, but in this range which we are interested, then there is always a divider, E, compute this delta. So delta is not just an infimum, but it's really a minimal. And particularly when delta is x is equal to 1, that just say uniform case stability is the same as case stability. Because originally it could happen that the infimum is equal to 1, but each term is larger than 1. But because the infimum is computable one of the term, of course, that's not going to happen. So this step is, you can think about it as an analog of the second step in the TOEI model, that instead of you test on all possible like real directions, you actually only need to test on the rational direction, on the directions coming from algebraic way. So I mean, this analog was actually well just defined, but I don't have time to explain more. But you can think about this as analog of the second step. And also we know that once you know it's computed by E, you can either show that the E actually give you a degeneration to some other KLT final variety X0. So in other words, it give you a special test configuration. So this is the equivalent analog of the toy model of step 2. So how about step 1? The step 1 was analytical work. That if I assume uniform K stability implies instead of K stability, in other words, you actually assume this like a stronger stability notion, then it implies the existence of a unique Klein-Stein metric. So this is like the analog that if I know the positivity of the derivative along all the directions, so the uniform K stability give you the positivity of all the directions, then F has a unique minimum. So this is the analog of the step 1. And to do this, let me just quickly say that they look at this completion of a space. The edge, of course, we want to study the space here, but since we want to do nonlinear PDE, you want your space to be complete with respect to some norm. And here, the edge is not complete. You have to do completion. And different completion using different norm will give you entirely different analytic theory. And here they do this like a PSH function theory, and then the right completion is E1. So basically then you put the step 1 and step 2 together, you solve this Yaltian-Donaldson conjecture, which say for any final variety, the existence of a unique Klein-Stein is equivalent to the K stability of X. So basically this characterizes how the final variety is. So there are 2 steps. The first step, you know, it has a unique minimum, implies is equivalent to the positive of along all the directions, including the real directions. And the second step, you tell you that the real directions actually the minimum is always algebraic direction. So as you heard yesterday in Karina's talk, for the smooth case, this was actually solved earlier by CDS and Sun, built on some like a Cheeger coding theory, and Secalidi later also has a similar solution. So, but this theory they use here is very different with the analytic theory itself is very different with the analytic theory which I just described. And also there was not much algebraic geometry in this here. So they also didn't actually use much algebraic geometry, unfortunately. And but the key regularity theory in their theory is that the Gromov-Hausdorff metric limit, if I have a sequence of Klein-Stein metric, so each of them is a metric space, I take a Gromov-Hausdorff limit. That's just a limit of a metric space, but it's actually a Klein-Stein variety. This is, of course, the key. I mean, also the cone angle version is definitely the most important recipe of the proof. So here, now we have this like a more general statement for singular one. I mean, we cannot prove the similar statement for singular one, but for our algebraic geometers, we only are interested in the algebraic geometry consequence. So in other words, we just want to show that if I have a sequence of K polystable final variety, there is always a limit, which is K polystable final variety. And this was proved by Blumer, Harper, Leisler, Yuchen Liu, and myself, conditional on the optimal destabilization theorem, which we proved later. I mean, I stated this later. So in other words, this optimal destabilization theorem is the one major recipe to prove that the K modular space is proper, it's compact. If I have a sequence of K polystable variety, there is a K polystable limit. And the uniqueness was also known. That was my work with Bloom. So anyway, so putting all of this together, although we don't know exactly this kind of result in the metric level, but we know this kind of result in the algebraic level, even for singular varieties. I mean, you know, if you are different geometers, I think it's pretty okay. You just care about the smooth ones. But for us, we really are interested in the singular ones. I mean, here, of course, for baryon geometry, we don't need too much justification for that. But for people who study moduli, I mean, since you want to study the entire modular space, it's definitely important to include all the possible singular ones as well. And as I mentioned, the second part of my talk, which is a technical cone of the method, is the higher rank finite generator, which I'm going to explain to you in 2 slides later. But let me just mention that the last analog that the Hilbert-Mumford criterion to say that I have this point which the weight is positive along all the C star direction, then it's GIT stable, it's on a moduli space. Now the analog is, if I have this K polystable variety, it should be on some moduli space, and then you have to construct this moduli. And this moduli is constructed. This is the K moduli theorem. So the first part, which basically say that if I look at the semi-stable one, they have the form of global quotient of a cost-projective scheme by some PGL n+1, by some general group, linear group acting on this. So to prove this too, prove this statement, you have to prove 2 things. You have to put the boundedness, and you also have to prove the openness. So the openness means if you have a family of Fano varieties, the K semi-stable one is open. So for the boundedness, it's not hard to show that it follows from the boundedness which all bidirectional geometers already know, like a BAB proved by Berka, or I think the Batayev conjecture is actually already enough for this. But for the openness, you really need the boundaries of complement to prove the openness, which I will explain a little bit more later. But this step, you need this. Berka's work, especially on this boundaries of complements. And then the second step is to show this stack indeed has a good modular space. This is a very subtle condition. If you study Dölling-Mumford stack, you know that Kyo Mori has a famous paper to say that Dölling-Mumford stack is, as long as it has kind of like a separated diagonal map, then it has good has cost-modular space. So, and also you realize that in your life, most of your Dölling-Mumford stack satisfy this condition. So they all have a cost-modular space. But that's not the case for Artin stack. Here the stack is the Artin stack. So for Artin stack has a good modular space. This is a very subtle property. So for example, if I consider just very naive example, like a A1 mod GM, then of course this has good modular space, which is just a point. But you actually identify 2 points, right? On the orbit, there is an open orbit and there is a closed orbit. You have to identify them. So it's not just pointed like the point here doesn't one correspond to the orbit here. The point here corresponds to the closed orbit upstairs. But if I have this P1 more GM, I throw in 1 more point, then this guy doesn't have a good modular space, because you have to identify. If it has, you have to identify 2 points upstairs. But the point here should one correspond to closed orbit upstairs. But you have 2 closed orbit upstairs. You cannot identify them. So this guy doesn't have a good modular space. So you easily see this is a very, very subtle issue. And fortunately, there is an analog paper by Harper-Leisler and Henlos to say there are 2 criterion. If it satisfy your good modular, your stack indeed has a separated good modular space, and you check that for the final word, and it does satisfy. But I think this is really the step which should convince everybody that at least when I studied this problem, this is a step which it really convinced me that the final K modular indeed has a good algebraic theory, because it really solves this uniqueness problem. Before, if we study degeneration of final variety, the major problem is you can always cook up some KLT final limit by using minimum program. But the subtle thing is usually you have a more than 1. So somehow the K polystability theory tells you, this kind of K stability theory tells you out of all possible limit, you can pick up unique one, which is the canonical degeneration. So this is the step which I think convinced me, or maybe many people, that there is algebraic theory behind. And we also know that the same point of this modular space precisely corresponds to the Karl-Einstein one. So we set up our goal to parameterize all possible Karl-Einstein final variety, and we complete our goal here. And as I said, the most difficult step, as usual, is to prove that this modular space is proper. So it's not the limit is not just unique, but it actually always exists. And then you go further to prove it's projective by showing some semi-line boundary example on this modular space. So basically, this entire theory tells you there is a K semi-stable stack on there, and then on the lower level there is a good modular, projective good modular space, and this there is a map between them. So now I switch to my more technical part of the talk, which is one key technical result we prove called higher rank fine generation. But let me first set up my problem. So now, the thing about for instance, as I mentioned, when you want to solve PDE, you have this space of Kähler potential, but it's not complete. So you want to complete it and then solve it, find some weaker solution, and then using prove some like a regularity to show those weak solutions indeed some satisfy smooth or some like a nice regularity issue. Here we do a similar thing, that we want to find this minimizer, but it's not good to start to work with the space of all divisor valuation. You'd better work on the completion of that, which is just the space of all valuations. So this one we know it's complete, and then you try to find the minimizer on the space of all valuations, and then you work hard to show that this space actually you can always find the divisor valuations. So in other words, this you have to do two steps. You first enlarge your space, find the minimizer there. So this is kind of a set up the theory, and then you do the regularity by showing that the minimizer is actually attained by divisorial, which in different geometry is the regularity. In our case, it's fine generation and plus boundedness. So you will see. So basically, we have this space of valuation, and we define this function A over S. And we already defined over divisorial valuation, and one can show that this definition can be extended to all valuations as long as you have this harmless assumption that the numerator is finite. And then for any valuation, we have this associated gradient ring, which is the integral domain because it's a valuation, right? We just look at for each fixed M, I look at the section. So I fix a lambda. I look at the subspace consists of sections with value larger than lambda. That's what I call F larger than lambda. Also, I can look at the space which is larger or equal to lambda. This is I call F lambda. Then I take the gradient ring just by take the quotient of F lambda modulo F larger than lambda, and I put all the lambda M together. I think we can either show this is a gradient ring, and because of V is evaluation, this is actually integral domain. And so the more technical result, which implies the optimal displacement theorem, is showing that when delta x is again with this harmless assumption for us, then for any valuation which computes delta, then the gradient ring is finally generated. So the first proof was given by Yuchen Liu and Zhiquan Zhuang. Later we found I think better proof, which I will explain, prove a stronger result using less. So that was that was also work with Zhiquan Zhuang, who is here. So once you have this, it's not hard to show that so basically this will imply that V is something called cosimonomial valuation. And then you can show that if you take a small rational perturbation of cosimonomial valuation, the over S is still attained, the infimum of over S is still attained, but this small rational perturbation is now is a divisorial valuation. So it gives you a valuation satisfy the optimal displacement theorem. So the upshot again is to prove that this string is finite generated, because this rational perturbation you can make it work only under the assumption that this is finite generated. Okay, now we come back to bilateral geometry. So more classical bidirectional geometry. So I mean, this is definition of Q complement. I think everybody here knows. So, and then Fujita, Odaka, Bloom-Janssen. This is the result which I mentioned. That we consider that so-called M basis type divider. So basically, I choose the basis of H0 minus MKX, and I put all of them together, the divider together. I sum all of them together. Then I average them such that they are basically minus KX, rationally minus KX. So basically, I divide them by the number of them times n. So this D is basically you can think about it as the linear combination of a basis of minus MKX divided by the right number. And now I look at the log-hand threshold of XD. And so here I fix M. This M is fixed. Now I just move my D, and I look at the log-hand threshold. I mean, this is in the finite level, so it's pretty easy to prove this. This guy is always attended by some divisor D, because now D is just moving in some like a finite linear system. And then one thing one can show is when delta x is less than m plus 1 over n, this is where the assumption comes up. Then the delta m is actually computed not just by, as I said, it's easy to show that this delta is computed by some a over some s for some divisor g, delta m, because that's in the finite level. But you just need to do slightly more work to show that a over this is actually computed by not just random e, but some e which is the LC place of some Q complement. So here you can just restrict yourself. Instead of looking at all possible e upstairs, you can just look at some of the e which are LC place of some Q complement, and that's give you delta m. And here is the boundaries of complement come into the picture. So we know that you can basically, once you fix the dimension, there is a fixed n such that if E is the LC place of a Q complement, then actually E is the LC place of some n complement. So here n doesn't depend on the complement, or doesn't depend on, actually doesn't even depend on the x. We made it only, mostly it doesn't depend on the divisor, the E. But I mean, the strongest result we know that the n actually only depends on the dimension of x. So in other words, now we are just trying to compute the minimum of delta of A over S for all the E, which E is actually LC place of some fixed linear system. So this is something much closer to what we studied. And so because of that, we know we can show that there is a sequence. I mean, you have to do more work, of course, but from this we know that there is a sequence of EM such that it has a limit which is a cosine monomial. I mean, you think about this EM, it's LC place of some n-bounded complement. So I can just resolve this n complement to make it a simple normal crossing. Then my divisor is kind of like moving around in a fixed dual complex. And then because dual complex is compact, then you just take the limiting point of this sequence of points in the dual complex. That's my V. So V, of course, is a LC V itself is actually LC place of some Q complement or some n complement. So particularly this will imply V is cosine monomial and it satisfies this minimum. So here we just got the cosine monomial one, but our goal is to get the divisorial one. So maybe here everybody know what cosine monomial is, but my definition is here that if I have some simple normal crossing model, I can, for any function, I can expand along some, if I take some strata on the simple normal crossing, I look at the generic point eta, and for any function, I look at the I expand this function around this eta. I got a power series. So particularly this like a beta. This beta is actually a tuple, depending on this r. So it's beta 1, beta 2, beta r. And for any fixed alpha, which is in with like non-negative coordinates, then I can define some like monomial valuation V alpha f monomial with respect to this v, y, and e, such that it's basically just the valuation on f is minimal of the pair of alpha beta for all the beta here. Here I already assume C beta is not equal to 0. So basically, if you think about the y and the e as a toric data, then this is precisely the toric valuation. So in general, we consider all the simple numerical crossing, and we consider all the toric valuations, or if you fix the toric data, then that's called the cosine monomial. And then their steps show, the minimizer is computed by some cosine monomial one. But the problem is the alpha here show up because it comes from a limit of a sequence of points. It could have a real coordinates. If it's rational coordinates, that's precisely correspond to divisorial valuation. But now I'm dealing with like a limiting point. So it could happen that it has real coordinates. Then you want to show that, but our goal is to show this kind of V, the gradient range is finite generated. That's our goal. As I said, if the V, if we know it's actually a divisorial valuation, if the coordinates are all rational, then the finite generation just follows from PCHN. So we're already done. But however, if you study general valuation, cosine monomial valuation, even it's a LC place of some valuation, the finite generation fails dramatically. So even in this case of P2, come up with a nodal cubic, if I have a P2, I have let's say I have something like sorry, this is not a nodal cubic. I'm sorry. This is a line with a quadratic. It's a nodal cubic line with a quadratic. I think in your example. Oh, okay. Sorry. In our paper, what? In our paper, it's nodal cubic, right? Okay. Yeah, but I know in your example, but I think in our paper, what's the example? It's P2 and okay, sorry, yeah. Sorry, that's not their example. The example I wrote on is actually in our paper, but they were the one first to find the first example. That's why I put their name there. So if you have another cubic here, and then if you look at all the valuations here, of course the LC place form a circle, cone over a circle. So this point correspond to this divider. And then if you blow up, you take any weighted blow up, you got some rational point here. And then the real ones are also LC place. And we know the finite generation one correspond to a range that all this part is finite generated. And all this part, the rational ones are finite generated, but the real ones are not. So somehow there's like a finite generation. If you just look at the property of finite generation one, it could be really complicated. In this circle, the non-finite generating one are precisely the non-rational points in this interval. So that suggests us we shouldn't just look at the finite generation one. We should look at the finite generation such that if you take approach of that, the approach is actually KLT. So if you just take the approach of adding LC place, if it's finite generated, we know it's going to be a semi-low-canonic, irreducible semi-low-canonic. But somehow, if you work on KSP program, that was the right degeneration you should look at. But for Fano, you should go one step further to try to describe all the KLT finite generation. And then you realize that all the degenerations in this range is a KLT one. But in this range, even the rational, as I told you, the rational ones, they are finite generated, but the finite generation is actually low canonic or semi-low canonic. So it's not KLT. So somehow for Fano, you really have to work on the KLT one. We spent a while to realize this, and then now that's our goal. And then we found that the right way to describe all possible finite generation valuation is I look at, so now I call it a special model or DLT Fano type of model. So basically I have a YE, which is a such that I can find a delta such that the ky minus e minus delta is ample and the ye plus delta is DLT. So I have an x, then I look at the DLT model final variety over this x. That's I call DLT final type model. And then there are two steps. First, we have to show any minimizer is indeed lived on this model. And the second, we have to show the valuations on this model give you finite generation. So in other words, for valuation exist on this model, even could be cosmonomial one, that was the biological condition we found to guarantee finite generation. I mean, in some sense, for this like case stability theory, for all the previous results, you just like work hard to develop the case stability theory. At some point, you make your statement to be birational geometry. Then you found that actually there are already birational, the known birational geometry results are enough to prove this one. But for this one, you really have to develop both sides. You have to develop the case stability theory to make a birational geometry statement. And then you also have to prove the birational geometry statement. The birational geometry statement you need is not in the basket yet. We have to prove. That's why this one is particularly challenging. And this is the birational geometry statement we found, that the valuation has to be on such kind of DLT final type model. And so actually that's our second statement. The first statement is the statement that say the minimizer always exists on such a model. And the second statement say, actually any valuation on such a model is finite generated. Actually it's stronger, because if you have this DLT final type model, if you look at all the LC places, the connectedness theorem usually implies that all the LC places form a simplex. So then the simplex, if you take adding 2 points inside this simplex, the gradient ring is isomorphic. Although the gradient might be slightly different depending on the number you choose, but the gradient ring structure itself is finite generated. So particularly if you take the rational one by BCHM, we know it's finite generated. So then we know adding one is finite generated. Adding final model. So adding final model. I mean, so the second statement is completely just about the final model. It's about like some final model live over X. The first one just say the minimizer exists on some final model. Yeah, the first one you have to choose. I mean, it exists on some final model. You prove that. And the second one just for any final model, there is a finite generation there. So, okay, I still have 30 minutes. So let's go even more technical. So let's try to look at the proof of the theorem 1, which says the minimizer exists on some special model or final model. So we already know V is cosmonomial. I mean, this is a step which I said before, use boundaries of complements. And then you first show that it's actually on some simple number crossing, some log resolution y prime e prime over x, such that you can find a complement D on x, such that the D has 2 properties. First, the value A, the V you look at, it's both a cosmonomial over the simple number crossing model, also a LC place of this XD. So it satisfies those 2 properties. And the second is that this is the perturbation property, which makes something like a tiebreaker works. That this D indeed is larger. If you take the Bayesian transform of this D on Y prime, it's actually larger than some tiny bit of ample divisor A. And this A is, I mean, general, so you can choose it down to the strata of E prime. So this D, I mean, of course, if you just have this property, it's a LC place and it's on some simple number crossing model. That was already proved, right? We already know that the minimizer is LC place by earlier work with Bloom and Yuchen. But here we actually, this like a tiny bit of A, which gives you room to do tie break, is precisely the room you guarantee that your degeneration is KOT instead of generally similar canonic. And so to prove this, you have to do some Diophantine approximation linearly, so similar as the one in the Hickman-McKinnon's paper, and also some global ACC, and some perturbation argument, which we already developed. And then, starting from this simple normal crossing model, you run some carefully choosing MMP, such that you can get a final type model. So somehow this condition will guarantee that you get a final type model. So if you don't have this A, then you precisely just got some you extract some LC place on some DLT model. But here you want to make it to be final, particularly then you need this A, and this like a small perturbation A there. So that's a first step. And then the second step is, of course, to prove that the finite generation holds. So actually, as I said, we actually aim to prove something stronger. We prove that for adding 2 alpha alpha prime, which is in the interior of your valuation, then the gradient ring are isomorphic. Actually, once you say this, you immediately realize this is just giving some like a toric degeneration picture over AN. So in other words, we actually prove something stronger. We prove there is a locally stable family X over AR with KLT fiber. And this is actually equirandom family. So this AR has a GMR action on that. That's a torus action on that. And on AR, the action is, of course, the standard one, but it also acts on the total family. So on total family, if you have a general fiber, then just move along with your T. But this action actually acts along the special fibers. And you actually show that the approach of the gradient ring is precisely just as a central fiber, so particularly finite generation. So actually, we prove this finite generation by finding the right degeneration. So this is not exactly the way, for instance, like a BCHM prove finite generation, but I think for the question we are interested in, I think this is the right way to prove finite generation. And so what's this, I mean, how this could work? So actually, without all this like a special assumption, if you just choose adding RLC place for some 1 Q complement, it's already enough to construct a equirandom family over AR. But again, the fibers could be semi-low-canonic, not KLT. So particularly, the fiber could be irreducible. I mean, if you just take one degeneration, if you start with divisor, if you take one degeneration, then because the gradient ring is always integral, that degeneration, even it's semi-low-canonic, is irreducible. But when you start to have a 2 divisor, then over the most deepest degeneration, usually it could be reducible, could be more than 1 divisor. So one thing you really want to work is you want to show in your setting that the central fiber is actually irreducible. And but actually one can show that as long if we know the central fiber is irreducible, this property which we are aiming to prove, then it works. So in other words, to prove this property, it's only suffice to prove the central fiber is reducible. So basically, let me explain this a little bit more. This picture tells you that the central fiber always exists, and it corresponding to some filtration, the gradient ring of some filtration. But that filtration is not necessarily the filtration coming from the valuation. So I think it's contained in the one coming from the valuation. But if you want to prove they are exactly the same, you have to know the central fiber is irreducible. And so that's where the special condition come up. So somehow we have to prove 2 results simultaneously. We first prove the result with what we want, but we also want to prove that not just our Kx can degenerate. So indeed, our entire special fiber over that, it also degenerates. So if I draw a picture, now let's say I have a E1 and a E2. So E1 gives me first degeneration is like this. So this is my X. This X1. But then I actually show that this E2 also degenerate on some DLT model. So that's the fiber-wisely, you also have a DLT model. So in other words, you have a E1, 2, which is the degeneration of E2 over X1 on the entire family. And then you can use this guy to degenerate again. So now I have a E2 over family. So I can do a family version of degeneration. So then this degeneration extends to A over A2. So I have a degeneration over a square. And you keep doing this step by step. And the key point is to show this degeneration for this divider commutes with you take a fiber. So if I restrict on the fiber, I look at the degeneration, which is the same as if I first take a degeneration and restrict on the fiber. For that is true, you have to have this special DLT condition. So if it's just low canonic, so once you can imagine if my divider here, when I take a degeneration, if it breaks into two divider, then this just fails. So you have to guarantee that your the divider here will degenerate on a special fiber. It's still one divider. It's still irreducible. And that's how the DLT picture and all the special condition come into the picture. Once you have that, then you can just keep doing, and then you get your result. So somehow this, okay, sorry, this is what I was talking about. So you first show that the degeneration induced commutes as with the fiber. That's T the fiber. So basically, and then you show because of this, once you take the degeneration, you first degenerate X, and then you can degenerate Y over X for it. And then putting that, you do induction on this too, you got the entire statement. Thank you very much. Let me stop.